This will be the second part of the Chapter 16 lecture. We stopped off with factors that affect acid strength. Now, the factors that we're going to look at will deal with the general formula for a substance as H bonded to X, X being some metal or non-metal group. And so, in order for the substance to be classified as an acid, we must have the polarity be such that the hydrogen has a partial positive charge and the other substance X have a partial negative charge. Now, if X is a metal, then this bond polarity is flipped, so the hydrogen is negative instead of being positive, and then you would write it as the positive substance first and the negative substance, which was the hydrogen, in the second spot. So, for example, we would have, instead of the formula HNA, we would flip it and have NaH. Well, this is a hydride, and we have that as one of the ions that makes a solution basic. So, in order for it to be an acid, the X substance has to be more electronegative than the hydrogen. And so the second thing that you need in order for the substance to be successful as being an acid is that this HX bond must be weak enough to be broken. And so the third thing, there's actually three factors. The third thing that makes a substance a stronger acid in a solution is that this conjugate base, this X minus substance, must be stable. In other words, you don't want the hydrogen to have a tendency of wanting to reattach to it once it falls off into the solution. So if you can make that X negative substance more stable, then it's going to be more acidic. And then we looked at the strength of binary acids next in class, and the acid strength actually increases as you go across a period. So if you're looking in period 2, that's the best example to see this trend. The bond polarity increases when you run across period 2. So when you have CH4, it doesn't have any acid or base properties, but when you get to group 5, the polarity becomes such that the hydrogen is slightly negative and the nitrogen slightly positive, and so it'd be a weak base. But when you get to hydrogen and oxygen bonded together, it's a neutral solution. And then when you finally get to group 7, as the acid strength is increasing as you run across that group, it becomes a weak acid. In the vertical columns, the acid strength increases as you go down a group, and the reason is because that H nonmetal bond is getting weaker, although it's still polar. And so you still need the hydrogen to be positively charged. And so if you look at group 7, HF is at the top of the group. It is a polar bond, but it's so polar that it's a strong HF bond. And so HF is classified as a weak acid, and HCl is a strong acid. Anything else below it would be a strong acid as well. So when you're looking at binary acids, their acid strength as you go across a period and down a group. So the second bullet point again is just reiterating the fact that HF is a weak acid because the bond is so polar that it's very difficult to break the HF bond. Now, the electronegativity difference between C and H is so small that the bond is nonpolar. So if you're looking at period 2, group 4 with C and H, it's neither an acid or a base. Now, the strength of oxyacids, we're going to look at the formula of Y bonded to O bonded to H. So oxyacids have a hydrogen-oxygen bond. Now again, we want that hydrogen to fall off into the solution as a positive ion, as a hydrogen ion. And so the strength of the acid is going to depend on the substance Y and what is attached to the element Y. Now if Y is a metal, which has low electronegativity, then the substance is classified as a base. So for example, if you have the Y substance being Na, then you simply have NaOH, which is sodium hydroxide. And so instead of the OH bond breaking, you have the NaO bond breaking, that ionic bond breaking, and then you have OH floating around in the solution, and it's classified as a base. If Y has an intermediate electronegativity, then the electrons between the Y and the O in the substance is what you're going to have stuck together, and then you can classify it as a weak oxyacid. If Y has a large electronegativity and the electrons are located closer to Y than to O, and the OH bond is polarized to lose the hydrogen more readily, then it's classified as a stronger acid. So if you can get that YO group to have more electronegativity and more polarized, then the hydrogen becomes more positive and it falls off more often. So if you look at the example down below with the picture, we have chlorine bonded to oxygen bonded to hydrogen, and then it's in equilibrium with the ClO group and then the hydrogen ion, and you can look at the Ka value as 3 times 10 to the negative 8th. The electronegativity of the chlorine is 3.0, and so there's a lot more electron drift towards the O and the Cl, and then the hydrogen falls off in the solution. If you look at iodine bonded to O bonded to hydrogen, then it's less likely to fall off because the electronegativity of the iodine group is only 2.5, and so this IOH substance is going to be a weaker acid. It has a Ka of only 2.3 times 10 to the negative 11th. So if you get more electrons drifting away from the hydrogen towards the oxygen and chlorine, then it's going to be a stronger acid. Now if you look at the next page, we're looking at the number of O's attached to this Y group. So if you have more if you have more oxygens attached to the Y group, then there's more polarity on that side, and then there's more electrons drifting away from the hydrogen. The hydrogen becomes positive and it falls off into the solution more often and makes it a stronger acid. So the strength of acids increases with the more oxygens. And so here's an example. You have hypochlorous acid, which only has 1 O, then you have chlorous acid with 2 O's, and then HClO3 is chloric acid, and that's on our list of strong acids, and then HClO4 has the most oxygens, and so you have the most electrons drifting away from the hydrogen. It makes the hydrogen ion more likely to be fall into the solution. So if the oxygens increase, then your acid strength increases. Now we're looking at the strength of carboxylic acids. So why do you have a COOH group capable of being ionized into an acid, but you don't have that for just a simple OH group? Well, the additional oxygen atom in the carboxyl group increases the polarity of the OH bond, and it stabilizes the conjugate base. And what I mean by that is that when the hydrogen falls off of the carboxyl group, you actually have a resonance structure. You have 2 oxygens dragging all the electrons towards it. The hydrogen falls off more often, and you have this resonance structure that is more stable than just a single oxygen group stuck to a carbon. And so the additional oxygens increases the polarity. The hydrogen ion gets into the solution more often than in the case of where it's just 1 O and an H. Now later on we learned that the single OH group in an organic compound is called an alcohol, and the COOH group we know is the carboxylic acid. So carboxylic acid strength also increases as you increase the number of negative groups stuck to the carbon. So this R functional group, as you get more electronegative substances on it, it would be more acidic. So if you look at this example, we have CH3 COOH versus CCl3 COOH. They both have the carboxylic acid group, but we're replacing the 3 hydrogens with 3 chlorines. Now we know that 3 chlorines has more electronegativity than just 3 hydrogens, so you have more electrons drifting away from the hydrogen towards the COO group being pulled along with the chlorines, and so trichloroacetic acid will be stronger than just acetic acid. On the next slide, we have our last classification of substances as acids or bases. So this is our last way to define acids and bases, and it's by a guy by the name of Lewis, and he came up with the Lewis dot structure. So we're going to be looking at electrons. And Lewis says that an acid has the capability of accepting an electron pair, and a base has the capability of donating an electron pair. And if you're noticing this, Bronsted and Lowry talk about protons being accepted and protons being donated, and so it's exactly the opposite for Lewis's definition. So instead of protons being donated, making it an acid, you have electrons being accepted, making it an acid. So this definition is a lot narrower in scope because we don't have to worry about a hydrogen ion. We just need to look at where the electrons are located. So it's the most general definition of all the acids that we have. And Lewis acids are typically substances that have an incomplete octet, like BF3. We have classified boron as the moron, as I like to call it in a previous lecture. So boron the moron only needs 6 electrons to be stable. So instead of having a complete octet of 8 electrons, it has a capability of gaining 2 more electrons. Well, this ability to gain 2 more electrons would be an electron pair acceptor. It classifies, or Lewis classifies, BF3 as an acid. Now Lewis acids must have a vacant orbital, which means it has to have some location where the electron pair can be donated. So here's a classic example. you have NH3. It has two electron pair. You have one electron pair, sorry. You have two electrons, or one electron pair sitting on the nitrogen, not bonded to anything yet, and you have BF3 with an incomplete octet. And when these elements, or when these compounds stick together, the nitrogen and the boron bond to form the compound NH3BF3. And since the nitrogen donated the electron pair, it's classified as a Lewis base, and since BF3 accepted the electron pair, it's classified as Lewis acid. Now typically compounds with multiple bonds act as Lewis acids because those double bonds can be broken and you can stick other electron pairs there. So here's an example of another Lewis acid. We have water and carbon dioxide turning into carbonic acid. So if you look at where the electrons come from, water actually donates two electron pairs to the carbon. The carbon double bond between the oxygens breaks, and then the electrons drift to the OH group. The hydrogen on the water actually drifts over to one of the other oxygens as well. But you can see that in the third picture right here, you have this electron pair that has been donated from the water to the carbon. So water is the electron pair donor, so it classifies water as a base. Lewis would classify it as a base, and the carbon dioxide molecule would be accepting the electron pair, and so it's the Lewis acid. The last thing is the hydrolysis of metal ions. Now we've talked about this before earlier in the lecture, and so if you look at a metal ion that has a positive charge, it's going to be attracted to water molecules via these lone pairs on the oxygen. So if you have a higher charge on this metal, and if it's smaller, then it can make a stronger connection to the water molecule, and both of these factors will increase the Ka value. So to summarize, if you have a small metallic ion, it's going to be more acidic, which means it's less basic. And if you have a higher charged metallic ion, it's also going to be classified as more acidic. Again, it's going to be less basic. So here's an example problem. If you have calcium ions in a solution and zinc ions in the solution, which one's going to be more acidic? Both of them would form a hydroxide when they react with water, calcium hydroxide and zinc hydroxide. So we're wanting to know which one is going to be more acidic in the water. Well, if you look at the size of the elements on the periodic table, calcium going from left to right on the periodic table, calcium to zinc, the atoms get smaller. So because zinc is smaller, it's going to be more acidic, and calcium will be more basic. So as you go across, the size generally decreases, and zinc would be more acidic. Now we should know that calcium ions, when you put them in a solution, are technically neutral. They can't really form calcium hydroxide because it's classified as a strong base. But anyway, if you look at the second example, we have calcium ions versus aluminum ions. So which one's going to be more acidic? Again, if you look at the periodic table, aluminum is going to be smaller, which makes it more acidic, plus aluminum has a higher charge, so you have a smaller, higher charged ion that's going to be more acidic in water. So it wins on both categories, size and charge. The last thing is just a picture of the attraction between the water molecule and the ions, and if you're, again, a bigger ion with less charge, you're going to be less acidic. If you're a smaller ion with more charge, you're more acidic. So that's the Chapter 16 Part 2 lecture.